Hello, this is Nicholas Hayek, and this is my final project for Math 387. Um, this project is focused on Bezier curves, and in particular, how one might control the local and global characteristics of Bezier curves. So first, let's talk about what and why one would use a Bezier curve. The inventor of Bezier curves, Pierre Bezier, was an automobile designer. And in his position, he would want to be able to mathematically represent his curves and sketches in such a way that these representations are easily computable, are replicatable, are intuitive to adjust. Um, and so he set out to invent a solution. So here we have a series of ordered points. We call these control points. They are vectors, usually in R2, but generally speaking, they could be in any nth dimensional space. And they constitute, when they're ordered, a control polygon. And so that's what we have here. And the Bezier curve, in theory, should be interpolating over these points, should mimic the shape of the control polygon. And so this is what that would look like. You can see that it interpolates the endpoints exactly, which is one of the characteristic properties of Bezier curves. And it looks quite nice. So first we have to talk about Bernstein polynomials before we get into Bezier curves, because this is, in essence, the machinery of Bezier curves. And so this is how they are defined. A Bernstein basis is a series of polynomials where they're indexed from I equals 0 to n as such. And you might notice that this is exactly, mathematically, what a binomial distribution in probability is, where t would be, in essence, the probability of your Bernoulli trial, and I would be how many successes you're looking for. So that's the analog. And as such, it shares a lot of these probabilistic properties, one of which being that it partitions unity. In other words, if you sum all of the Bernstein polynomials in a Bernstein basis over I, you will always sum to 1. And similarly, at any t, any one of these Bernstein polynomials will lie somewhere in the unit interval. So it's very much like an event in a probability space. If you plot and overlay all these Bernstein polynomials, you'll also notice that they're symmetric, which is to say that the value of a Bernstein polynomial at t and I is going to be equal to the value of the Bernstein polynomial at 1 minus t and n minus I. And last but not least, what we observed in the beginning is that these Beziers map the endpoints of a control polygon exactly, and that is rooted in this property, in that at 0 and 1, these Bernstein polynomials are just Kronecker delta functions. So they are 1 at I equals 0 and 0 otherwise at t equals 0, and they're 1 at I equals n at t equals 1 and 0 otherwise. The proofs for these are relatively simple. The first one being the partition of unity follows from the binomial theorem, which is fitting. For this fact that they lie in the unit interval, you can use a probabilistic argument or induction, but that's not quite worth writing out. For the symmetry argument, it really comes down to rearranging this binomial coefficient and bringing the n down. Really just algebraic manipulations. And to see that they evaluate the endpoints, essentially you just plug in for t equals 0 and t equals 1 and find that they are 1 at I equals 0 and I equals n, and that just follows from the fact that if you're evaluating at 0 or 1 for pretty much any I, one of these guys is going to be 0, except for the fact when I is 0 and this guy is 0 to the 0, or I is n and this guy is once again 0 to the 0. So this is a graphical representation of all these Bernstein polynomials in a basis. So as I say, the collection of polynomials constitutes a basis. And so it's useful to look at them all together. because this is what we're going to be working with when we construct Bezier curves. Here, in this one with 50 Bernstein polynomials, you get this useful change in color. The darker colored polynomials are what would be early or low I values, and the red polynomials are greater I values closer to n. And so if we were to associate each I value with a point, say a control point, this defines something along the lines of a preference function for those control points. So as I say, if we assign each Bernstein polynomial to a control point, these darker colored control points get higher weightings early in our ranging of t, and they get less priority as you continue towards 1. And then other control points, later control points, take over and become what essentially constitutes your entire Bernstein basis. And so that's the idea, is that this Bernstein basis can define preference. And so from that, we conclude something of a natural function. And this is the Bezier curve, the classic Bezier curve. And it is defined as we just described. You just map each Bernstein polynomial to a control point. And what you get is a weighting, a changing weighting between each of these control points that shifts as you range from t equals 0 to 1. And this Bezier curve inherits all of the properties that we observed in Bernstein polynomials. The two that are identical and really just a rewording are that these weights add to 1 and that all of these weights lie between 0 and 1. The actual analogs are these 2 points. Because the Bernstein basis is symmetric, it really doesn't matter if we list these from x0 to x5 or x5 to x0. In any case, it's going to be the same curve. So we can interpolate over n control points in one order or n control points in a reverse order, and you're going to get the same Bezier curve. And because the Bernstein basis, or rather the Bernstein polynomials, are Kronecker deltas at 0 and 1, we're going to evaluate our endpoints exactly. Graphically, this is obvious because we see that we get full preference on this darkest curve and full preference on this reddest curve, which dictate v naught and vn when it comes to control points. So for an nth degree Bezier curve, you're evaluating on a computer an nth degree polynomial. And especially as we are evaluating numbers in the unit interval, this lends itself to some numerical inaccuracies. Raising 0.05 to 25 if you have 25 control points is not going to be easy. And so we have de Castajo's algorithm, which essentially solves this for us. It was actually discovered independently from Bezier curves by de Castajo, and that was his formulation of Bezier curves when he first discovered them. What it essentially says is that we can linearly interpolate between each of our control points and then interpolate between those interpolations. In a sense, we can generate all these auxiliary points of interpolations until we can no longer interpolate. And that's viewed here. This is for t equals 0.3. And so you see we interpolate between our control points linearly and get these orange ones. And these orange ones lie 3/10 of the way down each segment. And then we get these points and interpolate between them, and we get the green segment. And those points lie 3/10 of the way down the orange segments. And so these are our auxiliary points here. And we keep linearly interpolating until we get to the end. And this seems very disjoint from the Bernstein definition, but it really comes down to actually a property of Bernstein polynomials, and that is that they can all be represented as linear interpolations between Bernstein polynomials of lower degrees. And so this is a key fact that will make Bezier curves much easier to compute. And when we talk about some variants of Bezier curves, they will all have something similar to this. And in effect, that makes our computation quite nice, because now we can work down until, in effect, n equals 0 and reach our point. Um, Another interpretation of de Castro's algorithm is that we are subdividing a Bezier curve into two different Bezier curves. All it takes to see that is just perform one iteration. Um, and so this curve splitting is especially useful when working with splines, for example. For graphing purposes and implementations, this algorithm right here is perhaps a better analog to de Castro's. It says the same thing, it's mathematically identical. But here, what we are doing is we are getting a control polygon, and we are going to reduce that control polygon to a secondary control polygon, which is made up of the linear interpolations that we were talking about. And so this orange controlled polygon and this green controlled polygon are those, and they are just positioned in space differently. It is the same algorithm, but it does lend itself to an easier graphical interpretation. And that is the algorithm that was used to generate this pretty image. Over which I'll put a video because, of course, you can animate this, and it looks really cool. You see the arms sort of spidering their way along the curve, and it's just lovely to see. So, using de Castro's algorithm, each time we perform an iteration, we are essentially doubling the amount of computations we have to do. We are sprouting out two more processes, and so you get this tree of increasing order each time. So you see this is not very time efficient. So you do save the numerical stability by not computing, say, a 25th degree polynomial if we have 25 control points, but now you're going to be performing 25 squared computations. And they're not hard computations because these are all linear interpolations. They're all just linear functions that you're evaluating, but there are a lot of them. And so depending on if your computer is great at computing a polynomial efficiently, maybe at even step sizes, which we'll talk about later, or if you're using splines, which we'll talk about very soon, which only require cubic polynomials, one might be better than the other. But it's a value judgment. So this now is where we'll spend the rest of the presentation, and it is on, in particular, how we control Bezier curves. Bezier curves, of course, are well defined. For any control polygon, you get a unique Bezier curve, but we might want to adjust that one because it might not suit our needs. And so in particular, we are concerned with how the Bezier curve reacts to an adjustment of control points. So we single out a particular control point, we perturb it by, say, delta, some real number, and we're interested in the infinity norm between the old curve and the new curve, and that'll tell us really how much influence we have over a Bezier curve. Of course, if we change these endpoints, then the curve will change in maximum exactly how much we change the endpoints. But for, say, one of these central control points, you might expect their effect to be dampened. This is really the one novel result that I couldn't find in the literature, but I felt was pretty obvious to conclude, and that is a relationship between perturbing one of your control points in R2 and the infinity norm between the old and new curves. And I found that the relationship was roughly the perturbation times the Bernstein polynomial of the index at which your control point is changed, evaluated at that index over n. And so this is a nice clean result that also has a nice clean discrete form when you break out all of the binomial coefficients. And that'll be useful when we start thinking about how in particular different types of Beziers, if we split Beziers, they will react to perturbations. So this is the proof of that fact. We use a form of a derivative that was shown in a paper by Joy, and you might notice that these are actually Bernstein polynomials themselves, and that'll be useful in the future. But right here we have the discrete written out form, and so we maximize that. And that maximum occurs at I over n. And from there, it's really just plugging that in for this infinity norm, because of course, wherever this maximum occurs is where the maximum of this difference will occur, because of the fact that these BKNs will come out and you'll just need to maximize this. And so we see that yes, this term is less than that for any t, and that's the result we were looking for. And so we can expand that out and come to this nice clean form. So now with that result, what do we have? We can look at the previous example and we can calculate exactly how much this perturbation for any perturbation delta will change our infinity norm. It's not written here, but it comes out to about 0.3 times delta. And that's not a lot of change. We might want to increase that. We also see when we change this second control point, it sort of has residual effects in the rest of the curve. And that's also not desirable. So now we have two things we want to fix. The first of which being that we don't want to affect, say, the rest of this curve. And we also want to have a greater impact on the end result. This form also suggests that as we increase the number of our control points, we're eventually going to get to a point where our perturbations have little to no effect. And so that's also not desirable. So we need to truncate these curves in some way. And so that's where splines come in. A spline is a nice and fancy word for something that is not fancy at all, and that's just cutting a Bezier curve into many smaller ones. In this case, we have a third degree Bezier, a cubic Bezier. You also have second degree Beziers, which are referred to as quadratic ones, and those are really the only ones you find. But we observe some immediate properties of this. It fixes the problem of global effect. When we perturb any one of these points, it's going to be isolated to this chunk of our spline, and so we won't get this residual change in the rest of the curve. The second thing is that if we increase our control points into some large unreasonable number, it will not matter for the effect of our perturbations. They will still have the effect that they will have anyway. It becomes irrelevant. And so we don't get a dampening. As we need to interpolate over more points, we can just slice it up and deal with each part of the spline. And the last one, which we use the equation that we got before to prove this, is that our perturbations are going to have a much greater effect now that we have less control points to deal with. For a cubic Bezier, we can see that besides having full influence on the endpoints, which is normal, on the central control points, we get about half of a perturbation back, which is good. And so we have now a bit more control over the shape of our Bezier. We have isolated control, and now we don't have to worry about how many control points we are dealing with. It does have some drawbacks, though, the first and most obvious of which being this pinch point here, this cusp. If you're Pierre Bezier and you're an automobile engineer or designer, you might not want your sketches to have really abrupt pinch points. You want them smooth. And so we need to now remedy this. So we've patched a few problems and now we have this new one. And so that is next up, is to fix these pinch points. We refer to the continuity, the geometric continuity, as G1 continuity or GI continuity. Reason being is that these are parametrically defined over the unit interval, and you also might be concerned with, say, how you travel along a Bezier curve as you compute it. Say, if you're a video game designer and these are being created and you have an object that's moving along with the Bezier curve, you might be concerned with that velocity as it's being computed. But here we're concerned with the geometric continuity, and so we want to fix that. The theorem is that if we make these surrounding points collinear, just the immediately surrounding points of a joint, then we will remove that pinch point. We will gain C1 continuity. And this is if and only if. And so this is what that looks like. We have the first part of the spline and the second part of the spline, and if you take away this control polygon, it almost looks like there is no spline at all. It's nice and smooth and doesn't look out of the ordinary. One immediate drawback we see is that now we have lost some control over where our points are. Now we dictate that this point, or this point, one of the two, has to be somewhere, and in particular has to be in line with the other two. And so that's now a new condition, but it's one that we impose to get rid of the cusp. And to prove it, we first consider this easier result, which is that the segments at the ends of your Bezier are going to be tangent to the Bezier itself, as in the segments of the control polygon. And we can see that here, that this segment is lining up nicely with this red line, and that this segment is lining up nicely, and it looks tangent, but you can prove that. And it comes down to this form of the derivative that we saw before. Now instead of expressing it with its t's and its i's and its n's, we're just representing them as Bernstein polynomials. This is a nice relationship that is very similar to the recursive one. You get a lot of these with Bernstein polynomials. They're just lovely functions. And so differentiating is easy, and we do so, and then we use the Kronecker delta property that we observed in one of the first slides to pull an n out and get a degree of freedom along with this segment. And so its derivative being equal to that shows tangency, and then similarly we show this for the rightmost endpoint at t equals 1, and show that it's tangent to the segment of the last two that's created by the last two control points. And so now that we have this tangency property, the collinearity property almost comes automatically, because now we conclude that these two derivatives are equal if and only if we have a relationship between this side and this side of the equation, and essentially you let your coefficient a in collinearity be the ratio between this term, and there you go. And it works vice versa as well. If you assume that they are collinear, then you can prove it for all a, and in particular you can prove it for the ratio of these two coefficients, and you're good to go. And so now we have a fix, in essence, for the problem of the cusp. And the other great thing about this fix, about this collinearity condition, is while we lose exactly where in space one of these points is, we can still control the distance at which it lands between this joint. We have a degree of freedom in that coefficient a, so we can make it as far as close as we'd like. Maybe not as close as we'd like, but you do still have that bit of freedom. And so now we have a nice locally controlled spline that does not have cusps, and from which you still have a little bit of control. And this is essentially what I was saying, is that now you can minimize to your preference the degree of freedom that you have. So up until this point, in our quest to change the character of our Bezier curves, we have been altering our control points and our control polygon. But this is not always ideal. We might want to keep our control data constant, and this is where shape parameters come in. And essentially these are coefficients which are attached in some way to each control point, and which affect what the interpolation, or how the interpolation will interact with these control points. And so there are many implementations of Beziers which use shape parameters, but one of the earliest examples are rational Beziers, which are defined here. Essentially, you compute a Bezier where the control points have each attached weights, and you put it over this coefficient, which is the sum of these Bernsteins and those multiplied by those weights. Importantly, we have that if all of these weights are equivalent to each other, we are going to reduce to a normal Bezier curve. And so this encodes something of orthogonality requirement with these weights. You're really only going to get so much change as the weights are differing from each other. If you have a particular weight that is much more positive than the others, then you're going to have an attracting force towards that control point. And similarly, if you have a weight that's significantly more negative than the others, then you'll get a repelling effect with respect to that control point. And so we turn to the example before, whereas previously we would pull down our control polygon to get this red curve to pull down. Now what we do is we just assign a slightly negative weight to V2, and that will achieve the desired effect. This example is a little deceiving in that at the outer reaches it lines up nicely with the blue curve, but changing weights will propagate throughout the entire curve for your entire unit interval. So typically, you might not get something as nice as we see here. So that problem remains, and there are, of course, rational Bezier splines, which will inherit the same properties of ordinary splines, and that now you have some truncated control. To compute a rational Bezier, we, of course, can use the original form and evaluate it as is, but there does exist a de-Cassageau type algorithm, and that is accounted for by this form of a rational Bezier. Essentially, you factor out this, which we call a rational Bernstein polynomial, and you see that a rational Bezier can be expressed as a sum of these rational Bernsteins times their control points. And so this is a nice and convenient notation, but rational Bernsteins also have a lot of the properties of normal Bernsteins, in that they interpolate the endpoints exactly, which we observe when we plot rational Beziers, and that they partition unity. And most importantly, that you can derive a recursive relationship between these rational Bernsteins and Bernsteins of lower degrees. And from that, you get a recurrence between rational Beziers and Beziers of lower degrees. And this is exactly the de-Cassageau algorithm we were searching for rational Beziers, and we can use that to compute to our heart's desire. This is what a rational Bezier might look like when you alter the weights of one of these central control points. So here we're altering the weights of W1 or V1 right here. When we make the weights a little more positive with this orange curve, we see some attraction with that point. This blue is a standard Bezier. Interestingly, this green Bezier, where the weight is equal to 0, looks like it's only interpolating between the first and last control points, and this is, in essence, what happens when you set a weight to 0. Your rational Bezier will skip over that in the summation. But it's not completely the same, only because now these Bernstein polynomials, while they ideally should be degree n minus 1, they're still nth degree Bernsteins. So you don't get a completely exact interpolation between the control polygon minus this, but you get something to the effect. And we see with negative coefficients, we get some ballooning and some strong repelling force with whatever control point we set that negative weight to. And so this is a sample of what that all looks like. The coolest thing about rational Beziers is that they can represent conic slices, exactly, circular arcs, hyperbolas, parabolas. And this is something that ordinary Beziers just aren't equipped to do. People have made really good approximations of circular arcs, for example, using splines. But as an objective, it's impossible. Penna and Patterson showed the results that these rational Beziers can represent conic slices exactly, and also the result that they're projective invariant. The proofs of these facts are a little out of the scope of this presentation and rely on some more advanced projective geometry. But we can still observe the result by making a quadratic spline where the weights of each central control point is equal to cosine pi over 4. In stitching this together, you might think that this looks like a circle, but it is in fact a circle. And to prove this, what we do is not anything particularly enlightening or clever. We find the origin and see that there's constant radius between that and each of our splines. We only show it for the top rightmost spline here. But it is indeed a circular arc, just by the fact that you get constant radius with the origin. And as I say, hyperbolas, parabolas, all the rest, ellipses, can similarly be represented. Now we're going to turn to the subject of alpha Beziers. Alpha Beziers accomplish something of global control, where they utilize one parameter, and this parameter somehow affects how the resulting curve will hug or be repelled by the control polygon. So we start with this definition of an alpha Bernstein polynomial, which is given as follows. And this is very much like an ordinary Bernstein polynomial in that it partitions unity, it evaluates endpoints exactly, it's symmetric, proofs of these facts are just a little bit more hairy than the usual proofs on account of all these coefficients. And furthermore, if you set alpha equal to 1, we observe pretty quickly that this is just an ordinary Bernstein polynomial. So equipped with these, we can form a recurrence relation, which is shown in car. And just like before, now that we have a recurrence relation between the Bernsteins, we can use a de Castrojoux type algorithm to compute them. And similarly, when we define an alpha Bezier as just the sum of these with their control points, just as before, we use de Castrojoux. And so now we have an analog. This is what these Bernstein polynomials look like for varying alpha values. Because alpha could be any real coefficient, as you grow it a little too large or a little too negative, you get really undefined, crazy rat's nest kind of behavior. But for reasonable values, what you observe are exaggerated peaks on each of the central control points. And if we increase the alpha value, you get even more exaggerated peaks. And we can conjecture as to what this is really doing. If each of these are assigned to a control point, what that means is that for any one of the middle t values in the unit interval, we are really going to be attracted one by one to each of the control points. We're going to hug tighter the polygon. And so now we have a Bezier curve, an alpha Bezier, where the red is a normal Bezier. And we see with slightly larger values, we attract a little bit towards the polygon, and with negative values and 0, we have a much weaker interpolation. As I say, once you get out of a reasonable limit of alpha values, this becomes a little bit crazy, and you get weird things going on. And because this is a recent invention, only come up with about 6 years ago, there's not too much in the literature about them or analysis on how they behave. They are just really cool. And so now we're going to try to generalize all the topics we've discussed to surfaces. We'd like to, as opposed to interpolating over R2, a series of control points, and create a line, we would like to create a surface or a curve of curves. And so that's where this comes in. This is called a tensor product surface. And what you can think of is evaluating a Bezier curve with this inner summation and getting from that some auxiliary points and using those as control points for your outer summation. And so in a sense, you are sweeping the inner Bezier over the outer Bezier and coming up with a surface. And so this maps the unit square onto R3. Of course, these G and H's, they can be pretty much anything. We have the rational Beziers we talked about, the alpha Beziers we talked about. We'll discuss splines when it comes to surfaces. There are really generalizations of all the topics we talked about. And computing them is easy. Because we have de Castrojoux type algorithms for all of the Bernstein bases we talked about, we can apply that to each of the summations separately, where we say run de Castrojoux on the inner summation with H, get from that vectors, call them W, and use those as control points for the outer summation and run de Castrojoux again. Because each of these algorithms independently runs in On squared, we're now going to get something on the order of On to the fourth. To implement a Bezier surface, the easiest way to do it is to create a grid of unit squares on the x and y plane. And so that's what we've done here. And then once we have a sufficient number of points, we can change their z values and get some actual curvature. And so that's what we have here. If we let G and H be Bernstein polynomials, as we discussed, we get interpolation over the grid. We can plug in alpha Beziers too, and observe behavior that's very similar to what alpha Beziers do as curves. When we have alpha less than 1, it doesn't have as strong of an interpolary effect, and with alphas being greater than 1, we get this ballooning. If you continue increasing alpha, it becomes meaninglessly exaggerated. And we could generalize this idea of splines to surfaces, where essentially instead of now stitching together curves of degree 2 or 3, we stitch together surfaces where we cap the order of each of our Bernsteins to 2 or 3. And so for a bicubic, so-called bicubic patch, we'd have n equal to 3, and that necessitates 16 control points. And for any k, we would require k plus 1 squared control points, just by this double summation requirement here. It's still mass unit square as ordinary Bezier surfaces do, and if we essentially get control points to be shared between different patches, different bicubic patches, we get a G0 continuous surface. When due, formulated a condition for smoothing this joint, just as we required collinearity between the adjacent control points. If we have coplanarity, if we let the tangent plane be continuous along the ridge, then we're going to have G1 continuity. For the only series of points that might not have G1 continuity would be this ridge. So as long as we fix that ridge, we would get a smooth, continuous Bezier surface patch. And so this is what that might look like with the example above, where we had alpha equal to 3, and we interpolated over that paraboloid type thing, and now we have them stitched together at their endpoints. This is not G1 continuous, but this is G0 continuous. There are no coplanarity conditions applied here. One of the interesting things that we can do is we can let alpha vary and observe some animation. And so this might have some unlikely applications. Suppose if you had a heart that was composed of different alpha Bezier patches, and you altered those alpha values over time, and you might get a pumping effect. But that's a little tangential for this, but still fun. Some remarks. Early on, we discussed Decassageau and said that because it's not very time efficient, if your computer is better at figuring out polynomials, especially high degree polynomials, you might be better off. Because we introduced the idea of splines, we've really reduced that problem to computing cubic Beziers. And that's not so far off from linear interpolation, which Decassageau deals with, but we can get even closer. And we can get closer because of the fact that we are using even step sizes in theory. There are adaptive step size methods that people have developed to optimize the areas of a Bezier where you might not have that much curvature. So you might define an inverse function that decreases your step size as you get more curvature. But in our case, we're assuming regular steps. And from that, we can define a difference function. Here we have an extended out cubic Bezier. This is nothing special. This is just what happens when you evaluate all of the binomial coefficient terms and you manually chug it out and see what it comes out to. And this is what it comes out to. And so now we want to create a function f, let's say, which evaluates the difference between the Bezier curve at a particular t value and the Bezier curve at that t value plus some even step that we know and we use. And here's what we end up with. We have the difference function f, and we plug it in. And we see where these coefficients land. In particular, because this cubic is going to cancel out with this cubic, these t's, you're going to reduce your third degree polynomial evaluation problem to a second degree polynomial evaluation problem. And so this degree reduction is going to make your explicit brute force Bernstein computation of a Bezier a little bit more attractive in comparison to the time inefficient Decassageaus. And so that's what we have here. We group all of these constants. In theory, we can pre-compute these. And so now that we have these constants, all we have to do is plug in for now a quadratic. So this has been my project. Over the last month or so, I've been investigating how Beziers are used and their design motivations, some of the mathematical background for them and the Bernstein bases. And I really narrowed into the topic of how we might want to control the local and global characteristics of Beziers. And we accomplished this through splines, and we deal with cusps, collinearity. We introduced rational Beziers in order to solve the issue of not wanting to change our control polygon, and also alpha Beziers for a simpler one-size-fits-all coefficient that can change how exactly the interpolation interacts with our data. And then we generalized all of these ideas to surfaces and ended up with an animated biquintic alpha Bezier surface patch. And that's sort of the conclusion, and that wraps up all of the topics we discussed. And last but not least, I just want to affirm that all of the figures and graphs and animations in this presentation and in my notes are all generated by me using NumPy and Python. So thank you for listening, and I hope you have a good summer break.